Hey, let's start today's class. This time, we will delve the formula for the strength of the built-in electric field and the width of the depletion region inside a PN junction under summer equilibrium when no voltage is applied. We will also provide a qualitative overview of the case when a voltage is applied to the PN junction to conclude the class. First, let's take a brief look at the Poisson equation, which is a useful method for finding the potential distribution when the charge density is given in semiconductor devices. The Poisson equation can be derived from Gauss' law. You may have learned about Gauss' law in general physics or electromagnetics. So, applying a Gauss' law to a volume, we obtain the following expression. So taking the limits as delta x approach to 0, we ultimately derive the following relationship from Gauss' law. Also, there is a relationship between the potential and the electric field. So we end up with the following relationship. So this relationship is known as Poisson equation. Therefore, if we can obtain information about the charge density, we can derive information. We can derive information about the electric field. Moreover, with information about this electric field, we can naturally obtain information about the potential, right? And thus, in interpreting semiconductor devices, efforts are directed towards obtaining information about charge density as it lead to acquiring information about the electric field and potential. So within the semiconductor devices, once we qualitatively determine where there are positive or negative charge, we can find out the charge density. Then, just by substituting it into the Poisson equation, allowing us to determine the electric field. And with this electric field, we can naturally determine the potential. And multiplying this potential by minus E give us the distribution of potential energy with respect to position, allowing us to draw an accurate energy band diagram. And from this energy band diagram, we can predict and calculate the movement of carriers. So this process is a method applicable to all semiconductor devices and will be repeatedly used in the future. Therefore, you will naturally become familiar with and apply this process. Now, what charged particles exists within a semiconductor? The most obvious ones are electrons and holes. However, it is crucial to note that in addition to electrons and holes, there are fixed charge within the semiconductor, right? So when calculating the charge density, it is necessary to sum. It is necessary to sum the concentration of mobile carriers and the charge created by fixed charge. If when combining all positive and negative charged entities, the charge density becomes zero, we refer to that region as the neutral region, and it satisfies the charge neutrality condition. Then let's analyze the p-n junction. First, we will consider the charge density in the p-n junction. In the p-n junction, carriers in the junction region diffuse and recombine, leaving behind fixed charge minus fixed charge of acceptor ion in p-type and plus fixed charge of donor ion in n-type. Then we define the width of the depletion region as xn for the n-type and xp for the p-type side with respect to the central junction. Therefore, if we graph the charge density profile as a function of position, it would look like this. In the n-type region, the depletion region, in the n-type, the depletion region will forms up to plus xn, and the charge density at that point is E and D. And in the n-type region, a depletion region forms up to minus xp, and the charge density at that point is minus E and A. Let's solving the Poisson equation for the p-type region. Since we are analyzing a silicon semiconductor, we can use the permittivity of silicon. The Poisson equation. The Poisson equation is a simple first order differential equation, and because rho and epsilon are not functions of position, we can easily find the electric field. When solving the differential equation, an integration constant appears here. It's need to be eliminated using boundary conditions. So considering the boundary conditions, the electric field is formed. The electric field is only formed in depletion region, right? Because the fixed charge are exist in this depletion region, so the electric field will be formed within the depletion region. And outside this region, the electric field intensity is 0, right? So therefore, applying the depletion approximation, we obtain the boundary condition that the electric field becomes 0, at x equal minus xp. Finally, we can derive the expression for the electric field in the p-type regions as follows. A similar process can be used to derive the electric field in the n-type region. If we plot the electric field graph obtained in this way, we will see the electric field in the p-type and n-type regions as follows. Notice that electric field is maximum. Electric field is maximum at x equal 0. The region all values of the electric field are negative is because we positioned the p-type on the left and the n-type on the right, causing the electric field form from right to left in the negative direction. Another observation is that the electric field must be continuous at x equals 0, the junction point. So applying the continuity condition to the E field expression, we can simplify it to the following relationship. The products of doping concentration and the depletion region width is the same for both sides. That is, increasing the doping concentration leads to a narrower depletion region, and conversely, lower doping concentration results in a wider depletion region. So this relationship is derived from the continuity condition of the electric field at the junction. So through this relationship, we can deduce another fact. In the charge density profile, the depletion region width in n-type region is xn, and the charge density at that point is E times nd. Therefore, the area of this rectangle is given by E nd xn, right? And similarly, in the p-type region, the depletion region width is xp, and the charge density at that point is minus E Na. So the area of this rectangle is E Na xp. And since NaXP and NDXN are equal, we can conclude that the area of these two rectangles are always equal in the charge density profile. Then let's apply this fact to the one-sided junction. For example, consider a P plus N junction. In this case, we can easily predict that the charge density profile will have a narrow depletion region due to the high doping concentration in the P-type region. Therefore, XP will be close to 0, and due to the large Na, a charge density profile of a thin and long shape will be drawn. The same area will be represented in the N-type region's charge density profile. Continuing, let's proceed to find the potential distribution. The potential can be obtained by integrating the electric field with the negative sign, so it results in a quadratic function, right? So it results in a quadratic function. Again, there will be an integration constant, so we need boundary conditions. Since potential is a potential difference with respect to some reference point, we can arbitrarily choose the reference point. Therefore, let's define the potential at the depletion region boundary in the P-type region, where x equal minus xp as 0 volt. Since voltage is the potential difference with respect to an arbitrary reference point, such an assumption is permissible. So using this boundary condition, the integration constant becomes 0. And we can find the potential in the P-type region. Then the same approach can be applied in the N-type region, but in this case, we need to apply a different boundary condition. The potential at x equal xn in the N-type region differs by VBI. So it is VBI, the built-in potential from the potential at x equal minus xp. Therefore, utilizing the boundary condition that the potential at xn is equal to VBI, we can find the potential as follows. And finally, since it must be continuous at x equal 0, we can use these conditions to find VBI. So these continue can be derived the VBI. So please note that the potential being a quadratic, it is a quadratic function in x will have a parabolic. So actually it looks like in this way, it being a quadratic functions in x will have a parabolic shape on the graph. And next, let's calculate the width, of the depletion region. The potential must be continuous at the boundary, which is x equals 0 between the p-type and n-type regions. So utilizing these condition, we can derive the following relationship. So we just put here 0 and 0. We can find out this relationship. Additionally, since NAXP and NDXN are equal, we can use this information to deduce XN and XP. So by using this relationship to here, we can find out this one and this one, right? So we can finally express as follows here. So therefore, the total depletion region width is the sum of XN and XP, right? So we can express as follow here. And as previously inferred, it is confirmed that if it is confirmed mathematically that as the doping concentration increase, the depletion region width will be decreased, right? And now let's apply these to the one-sided junction. So let's think about one-sided junction. In the case of a P plus N junction, the acceptor concentration is much larger than the donor concentration. Since Na is very large, this term is going to be 0, right? This term converts to almost 0. Therefore, the expression for the depletion region width is as follow here in case of P plus N junction. And in the expression for Xn, assuming that Na is very large, allow us to approximate this expression in the same form, right? Thus, we can conclude that the depletion region width is approximated to Xn. And conversely, Xp also converges to 0 because Na is extremely large, making the denominator approach to 0. Therefore, the total depletion region width is determined by the low doping concentration. So it is low doping. Since it is a P plus N junction, so it is the depletion region width will be determined by the low doping concentration in the N-type region. So in the case of an N plus P junction, it would be opposite. So I encourage you to try deriving it by yourself. Now let's determine the maximum value of the electric field in the PN junction. It has been mentioned that the intensity of the electric field is maximum at the junction where x equal 0. So to calculate this, we can substitute x equal 0 into the expression for this electric field, and using the term xn and xp that we derived earlier, right? But secondly, if we know the relationship between the electric field and potential, that allows for a more straightforward calculation. Integrating the electric field in the depletion region. Integrating electric fields in the depletion region will eventually result in VBI, the built-in potential. Since the built-in potential represents the internal potential difference, so this is an expected outcome, right? The absolute value is used here to avoid concerns about the sign. So in this context, the profile of the electric field resembles a triangular shape. So the area under the triangle becomes the built-in potential. Considering that the base of the triangle, base of this triangle will be this one will be depletion width, right? Xn plus xp will be depletion width, and the height is the maximum value of electric field. We can calculate the area as follows, right? Therefore, the maximum value of the electric field can be obtained as W divided by 2VDI, and when simplified, the following expression can be derived. So when studying semiconductors, it is crucial to understand these relationships rather than memorizing formulas. There are many aspects that can be more easily calculated when understanding these various relationships. So practicing to derive such contributes to a deeper understanding of semiconductor physics. Let's summarize the concepts we've learned so far. Consider a situation where the left side is p-type and right side is n-type, examining the thermal equilibrium state first. In this scenario, the Fermi level will naturally be maintained horizontally, right? Because it is a thermal equilibrium. Although electrons on the right side attempt to diffuse to the left, but a built-in electric field arises. As a result, the force of electrons attempting diffusion and the force of throughput caused by these. So this electric field force will be caused by this field, this built-in electric field precisely counterattack
counteract. They are counteract each other. So this equilibrium prevents the mobile carriers from undergoing net transport, leading to a current, no currents flow in the summer equilibrium state. Alternatively, you can understand that when a PN junction is formed, the built-in potential acts as an energy barrier. So that's the electrons here find challenging to overcome, preventing the flow of current. So this is what we've learned so far. And finally, let's consider what happens just qualitatively when a voltage is applied to this PN junction. We will apply a positive voltage to the p-type region relative to n-type region, which is known as forward bias. In this case, applying a positive voltage causes the energy band of p-type region to shift downward. Why does applying a positive voltage lead to a downward shift of the bands? Energy bands represent the distribution of potential energy, right? Minus QV. So applying uh, a positive voltage results in a decrease in potential energy, which means causing the band to shift downward. So if you think about this slowly, it should become understandable. As a result, when a positive voltage is applied, the band shifts downwards, the PN junction goes out of the summer equilibrium state. So in chapter 6, we discussed the analysis of such non-equilibrium semiconductors. So under the non-equilibrium conditions, the single Fermi level for electrons and holes in equilibrium gets split into two quasi-Fermi levels, right? So in the case of forward bias, and in this case, this one going to be VBI. So VBI decreased significantly when compared to summer equilibrium. So from the perspective of electrons, the height of the energy barrier has decreased, making it relatively easier to cross. So when you compare this diffuse and this diffusion, electron can be more easily diffused under the forward bias, right? Therefore, under forward bias, the lowered energy barrier induces electron movement, leading to the generation of current. Next, let's consider the opposite scenario. Let's apply a negative voltage to the p-type region relative to the n-type region, known as reverse bias. When a negative voltage is applied to the p-type region, the band shifts upward. The band shifts upward at this time compared to the equilibrium state. Also, entering a non-equilibrium state due to the applied voltage cause the Fermi energy to split into two quasi-Fermi levels. In this case, VDI has increased, making it more challenging for currents to flow. Thus, under reverse bias, current does not flow well, and under forward bias, current flows, demonstrating diode characteristics where current exponentially increase with positive voltage and does not flow well with negative voltage. So further detailed analysis can be learned in the next semester through the semiconductor devices. In summary, throughout this semester, we examine the carrier distribution, mobility, and diffusion in equilibrium and also non-equilibrium states for independent p-type and n-type semiconductors. In this chapter, we explore the phenomena occurring at the junction when these two types of semiconductors come together. When materials with different Fermi energies forms a junction and reach thermal equilibrium, a phenomenon of carrier depletion occurs at the junction. We investigated the charge density, electric field, potential, and energy band diagrams in the depletion region. This understanding will serve as the foundation for analyzing the electrical characteristics of many semiconductor devices formed by PN junctions in the future. That concludes our lectures for this semester. Well done, and thank you for your hard work. Thank you.